Griffiths E&M section 3.4.1, continuation of multipole expansion. So we did example 310 in the previous video, but that was only for finding the potential from two charges. One was a plus charge, one was a minus charge at some position away from those charges. Okay, so we're going to generalize that in this video and say, all right, I have some charge distribution. Don't know what it is necessarily. I will pick an origin for my charge distribution, and I will say that I want to find the potential at some point P in space. All right. By definition, this is our vector R, and I have charges all over the place. Let's pick this little chunk of charge. That is my vector R prime, and therefore the vector that connects my charge bit to the region of space that I care about is script R. I'll also say that I need to have an angle here between those two vectors of alpha. All right, I can go ahead and write what that expression is for the potential. You've seen this before, 1 over 4 pi epsilon naught. The integral of all of my charges which exist at the prime coordinates integrated over all those primed coordinates. Okay, so just like last time where we focused on this script R vector, let's go ahead and define what that is again. Script R, using the law of cosines, is going to be R squared plus R prime squared plus 2R R prime, it's a minus sign rather, minus 2R R prime cosine of the angle between them, which is defined as alpha here. Okay, the same trick as last time. I pull out an R squared, 1 plus R prime squared over R squared minus 2 R prime over R cosine alpha. Okay, I'm going to define something even further. This is R squared 1 plus R prime over R prime over R minus 2 cosine alpha. I'm going to call this bit here epsilon because it's small. Okay. I'm imagining that I'm looking in a regime where I'm looking far, far away compared to the distances that are separating my charges in my charge distribution. Okay, so notice I still have equal signs everywhere. And at this point in time in the last video, we had truncated our sum to remove one of these, or truncated our terms to remove one of them. Okay, then the strategy last time was to say, all right, we have a value for R. Now let's find a value for 1 over script R. Okay, so I will go ahead and do that. 1 over script R then becomes 1 over R times 1 plus epsilon to the minus 1/2. Okay, 1 over R, doing the binomial expansion, except now I'm going to keep all of the terms. They're an infinite number of them, so I won't write all of them down. 1/2 epsilon plus 3/8 epsilon squared minus 5/16 epsilon cubed plus blah, blah, blah. All right, and now what I can do is I can go ahead and plug in the value for epsilon, which is this chunk over here. Do some math if you want to. You can follow along in the book. I'm not going to do all of those math steps. And then rearrange everything. And I get something that looks like 1 over r, 1 plus r prime over r times cosine of alpha plus r prime over r squared times 3 cosine squared alpha minus 1 over 2 plus r prime over r cubed times 5 cosine cubed alpha minus 3 cosine alpha over 2 plus blah, 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 blah. I notice something immediately. I have this repeating bit here, r prime over r, with sequential powers associated with it. And I'll notice that I have some other thing that's kind of repeating in maybe a familiar way, something that has powers of cosines in it. All right, those are your Legendre polynomials. So I can go ahead and write 1 over r as 1 over script r as 1 over r times a sum from n equals 0 to infinity of this first factor, r prime over r, to the n, right? That captures the right bits, times my Legendre polynomials Pn of cosine of alpha. Right, therefore, I can plug this expression for 1 over r to get something that is still exact for my potential. 1 over 4 pi epsilon naught. I want to take the sum of n equals 0 to infinity, 1 over r to the n plus 1. All right, I took this r to the n outside and combined it with this because I can. And the reason I can take it away is because it does not need to be integrated over because I'm integrating over the prime coordinates only. So I still have r prime to the n inside times my Legendre polynomials of cosine of alpha. Right. This, because cosine of alpha represents some relationship between the primed coordinates and the region of interest, the unprimed coordinates. So that can't leave the integral. Times my charge density, wherever that is, integrated over all of those charges. This is the multipole expansion. Where each value of n represents a different element of the multipole. So for n equals 0, we have a monopole. For n equals 1, we have a dipole. For n equals 2, I believe we have a quadrupole. All right, and it keeps going on and on and on. All right, so if you could evaluate this integral for all n to infinity, you can calculate the exact value. We're not going to do that most of the time. We're going to say, all right, what's the first non-zero term, or what's an approximation for the potential? But we couldn't have calculated an approximation for the potential just from this expression here.